Ever wonder how your car can see things that you can't? Well, today we're going to break down the brilliant science behind modern radar, the tech that's basically giving our devices a kind of superpower. I mean, really think about that for a second. How can a car possibly know with pinpoint accuracy that there's another vehicle up ahead when you, the driver, can't see a single thing? It feels like magic, but I promise you, it's just really, really cool physics. The secret is a technology called frequency modulated continuous wave radar. Yeah, that's a mouthful, so we'll just call it FMCW radar. And the way it works is by solving a series of clever little puzzles. So in this explainer, we're going to solve them right along with it, one by one. Okay, so let's tackle the first and maybe the most fundamental puzzle of all. How in the world does a radar know how far away something is?
It all starts with something called a chirp. Now, this isn't a sound, it's a radio signal. And its special trick is that its frequency is constantly climbing. For instance, a typical car radar sends out a chirp that sweeps all the way from 77 to 81 gigahertz in just 40 times millionths of a second. This little chirp is our most basic tool.
So here's the basic idea. You have a transmitter, the TX, that sends this chirp out into the world. It zips along at the speed of light, smacks into an object, say, the car in front of you, and a tiny piece of that signal bounces back and gets picked up by a receiver, the RX. Simple enough, right?
But here is where the magic happens. Because the radar is still sending out its original chirp, when the reflected one gets back, there's a slight time delay. And mixing those two signals together, the one going out and the one coming back, creates something totally new, a signal with a nice constant frequency.
We call this new signal the intermediate frequency, or the IF signal. And here's the absolute key. The frequency of this new signal tells you the object's distance. A higher frequency means a longer time delay, which means the object is farther away. It's that direct. And just like that, puzzle 1 is solved. Okay, so we can see one object. That's great. But, the real world is messy. What happens when you've got multiple cars, signs, maybe a pedestrian, all at different distances? Well, when there's a bunch of stuff out there, you get a bunch of reflections coming back. The radar doesn't get that clean, single-frequency signal anymore. Instead, it gets this jumbled-up, complex wave that's a mix of everything. Honestly, it just looks like a mess of noise. So how do you make any sense of that mess? You use an absolutely brilliant mathematical tool called the fast Fourier transform, or FFT. The best way to think of it is like a prism for radio waves. You know how a prism takes white light and splits it into a beautiful rainbow of individual colors? Well, the FFT does the exact same thing to that messy signal. It splits it into all the individual frequencies that are hidden inside. And the result is, well, it's pretty incredible. After running what we call a range FFT, that messy signal transforms into this clean, beautiful graph. Each peak on the graph represents one specific frequency, and since we know that frequency equals distance, the number of peaks tells us exactly how many objects the radar is seeing. Problem solved. All right, we are on a roll. We can now see multiple things at different distances. But what happens if two cars are right next to each other at the exact same distance from our radar? Uh-oh. This is a big problem. Since both cars are at the same distance, they create the exact same IFS signal frequency. So our amazing range FFT tool, the one that just worked so perfectly, just lumps them together into one single peak. As far as the radar is concerned, there's only one car there. It is completely blind to the second one. So how do we solve this? The secret lies in a different property of the radio wave. It's phase. You can think of phase as the precise starting point in a wave's cycle. While frequency is great for measuring the big changes that tell us about distance, phase is exquisitely sensitive to microscopic shifts. And those tiny shifts are the key to unlocking an object's velocity. So just how sensitive is it? Get this. If an object moves just 1 millimeter between two radar chirps, that's about the thickness of a credit card. The phase of its reflected signal will shift by pi radians. That's a massive 180-degree flip. It is an unbelievably sensitive measurement. So the radar doesn't just send one chirp. It sends a whole sequence of them, one right after another. And by carefully tracking how the phase of the reflection changes from chirp to chirp to chirp, it can calculate that object's speed with incredible accuracy. And this brings us to our next amazing tool, the Doppler FFT. We run a second FFT, but this time we're not looking at frequency anymore. We're running it on all the phase data we just collected. And poof! It separates that single distance peak into multiple new peaks, one for each unique velocity. Now we can finally tell those two cars apart, because one might be going just a tiny bit faster than the other.
So, what's the final boss level? You can probably guess. What if you have two objects at the same distance moving at the exact same speed? Our range FFT sees one peak. Our Doppler FFT sees one peak. How on earth do we see them both?
The solution, once again, is actually beautifully simple. We just give the radar more eyes, or in this case, more receiver antennas. Check this out. Because the receiver antennas are physically in slightly different spots, a reflected wave will hit each one at a microscopically different time. This super tiny time difference creates a phase difference between the signals each antenna sees. And by measuring that phase difference, the radar can calculate the object's precise angle. We call this the angle of arrival. Now, this alone is a massive leap forward. But engineers, being engineers, figured out a way to level this up even further with a cool technique called MIMO. That stands for multiple input, multiple output.
And this is where the genius of MIMO really shines. Just look at this comparison. A standard system with 9 antennas might get you an angular resolution of about 14 degrees. But a MIMO system with only 6 total antennas actually gets a better resolution of about 12.5 degrees. It does this by creating what's called a virtual antenna array, which gives us better vision with less hardware. How cool is that?
And there you have it. All the puzzles are solved. The range FFT uses frequency to get distance. The Doppler FFT uses phase changes over time to get velocity. And a final angle FFT uses phase differences across antennas to get direction. You put those three things together, and you've built a complete, detailed, three-dimensional map of the world around the car.
So when you really step back, what we've done is taught a machine how to see with radio waves. We've shown it how to turn a jumble of noise into a rich 3D map, all using some clever physics and math. It really makes you wonder, now that we've given our technology superhuman sight, what other senses are we going to build for it next?